We have seen that the second part of the fundamental theorem of calculus provides a very convenient method for evaluating the definite integral of a function, assuming that we can find an antiderivative of that function. Now what we need is a convenient notation for antiderivatives that makes it easier to work with as well. And that notation is called the indefinite integral. And it is written like this. Integral of f of x dx is equal to the capital F of x, where the capital F of x is the antiderivative. And this means that if I take the derivative of capital F of x, I get f of x. It is important to denote the difference between definite and indefinite integrals. A definite integral, such as the integral from a to b of f of x dx, is going to be a number. Whereas an indefinite integral, so without the upper and lower limit, f of x dx is going to be a function. Or, as I stated before in previous videos, a family of functions. The connection between them is given by the fundamental theorem of calculus, part 2. Now, if f is continuous on the closed interval a to b, then the integral from a to b of f of x dx is equal to the integral of f of x dx from a to b. So let's take a look at some examples. So we have the integral here of the first one, and we're going to rewrite this as 5x cubed over 3. So remember, we add 1 to the exponent, minus 4x squared over 2. And if you recall, what function do we take the derivative of to get 1 over x? And that will be the natural log of x. And then don't forget, because we're finding the general indefinite integral, we also need to add c. And I'm just going to do a little bit of simplifying here, because I can simplify my second term to be 2x squared, and then plus the natural log of x plus c. All right, let's take a look at another one. So the integral of e to the x minus 9x to the negative 2. Remember that e to the x is a great one, because the integral of e to the x is e to the x, because the derivative of e to the x is e to the x. And then we have minus 9x. We add 1 to the exponent, so that would be negative 1 over negative 1, and then plus c. So this will be e to the power of x plus 9. Notice the 9 doesn't move because it doesn't have a negative exponent, so only the x moves to the denominator, and then plus c. So most of this is review. There might be a few new antiderivatives that we haven't done before. All right, so let's contrast that with this example here, where we're going to evaluate the integral. So before I do that, I would like to make both of these exponents to be negative, so that I'm not going to be working with fractions. So I'm going to add 1 to my exponents. So I get x to the negative 1 over negative 1 minus x to the negative 2 over negative 2. So really this is going to be positive, and I'm going to evaluate from negative 2 to negative 1. All right, so if you don't like how this is rewritten, let's just rewrite this as negative 1 over x plus 1 over 2x squared from negative 2 to negative 1. All right, so we're going to plug in negative 1 first. So when I do that, I get this, plus 1 over, so when I plug in negative 1 here, I get that. And then minus, plugging in negative 2, I get negative 1 over negative 2, plus 1 over 2, negative 2 squared. All right, so simplifying, we get 1 plus a half, minus a half, and plus an eighth. So the half minus half is 0, so then we just have 1 minus 1/8, which is 7/8. And you can try the other ones on your own.